All right, in this final section of this advanced organic reactions unit, we're going to discuss reactions of alkanals, alkanones, acids, and alkanoates. Let's start with the preparation of acids from alkanals and alkanones through oxidation. Alkanals can be oxidized with the help of potassium KMnO4 or K2Cr2O7 to acids with the same number of carbon atoms. So take a look here. This is an alkanal. You can see at the terminal carbon we have C, single bond to an H, double bond to an O. C, single bond to an H, double bond to an O. In this case, I only have 2 carbons. In the top case, I have 2 carbons plus some additional alkyl group, R. Okay, we don't need to draw the whole thing. We just need to draw the end. So what happens here? Well, in the presence of either of these catalysts, we get the same number of carbons. So if we count here, it's 1, 2, 3, 1. So whatever the R group is, it could be 1 carbon or 5, whatever. 2, 3. In the second one, we have 1, 2 carbons. Here we have 1, 2 carbons. And so just for the sake of visualization, let me draw the structure of the starting product and the ending product for the one on the bottom, just so it goes with the reaction as we see it. So what are we doing here? Well, we're keeping, oh, I missed a carbon. So let me fix that. I have 2 carbons. C, double bond O, H, goodness. All right, so this is this starting product here. Now, we have an oxidation of this alkanal to produce an alkanoic or carboxylic acid. So this parent structure remains the same. This double bond remains. But now we have OH. Okay? So this oxidation occurs with the help of either of these compounds. Okay? Now, if I had more carbons here, like here I have CH2, COOH, and then this single bonds to whatever additional alkyl group is in that parent chain. Okay, so that's how that looks. We can also easily oxidize alkanones. Remember that alkanones are where the carbonyl group sits in between 2 alkyl groups. One we call R, one we call R prime. And the reality of what happens here in this oxidation is that there's a cleavage that happens on either side of the carbonyl group. So we either cleave here, and if we do that, we get this carboxylic acid that involves R. So instead of this bond to R prime, then we would get OH and get this carboxylic acid. Or we could cleave here, okay, and get the carboxylic acid that involves R prime, and we would bond to OH here, okay? So either of those can form. We can get a mixture. Some of it depends on the conditions. But you can always be sure that you can show one of the products if you just cleave on that double bond. So if you look at the second example, so this is our R, this is R prime, right? So if I cleave R prime, then I lose one of those. I lose my methyl group, and I would bond it with an OH. Okay, so CH3, CH2, C, double bond O, OH, and that's the product that we've shown here. Okay, the same thing is happening in this one. We just have more carbons in our R chain. Okay. All right, another way that we can prepare acids, we just talked in the previous couple slides about oxidations of alkanals and alkanones. We can also prepare carboxylic acids or alkanoic acids by fermentation. If we have, we can start with an alcohol in air with the help of something called an acetobacter bacteria. So I've started here with the fermentation of ethyl alcohol, ethanol. There's a two-step process here. Step one is the formation of this alkanal. Okay. And then from there, in the presence of that same acetobacter bacteria, we get our alkanoic acid. Okay. So notice here we still have 2 carbons. Okay, we're just decreasing the number of hydrogens here to form the double bond with the oxygen. So here we have CH2 single bond OH. Okay. Here we have that same carbon now, CH double bond O to that CH3 group. And then the last step is C double bond O OH. Okay, looks like that in a 2-step process. So we've talked in this section so far about the formation of these alkanoic or carboxylic acids. But let's talk now about reactions involving those acids, if we have them or once we form them. So the first reaction involving an alkanoic acid is salt formation. All alkanoic acids react with alkali metals to form water-soluble ionic salts. Salts from higher alkanoic acid members are also soluble in water. So you can form a water-soluble ionic salt in reaction with an alkali metal. The second type of reaction that acids can participate in is reduction. So in this first example, we have some R group, some alkyl group, and then our carboxylic acid. And the reduction occurs to produce this alcohol. And then also here, this carboxylic acid reduced to an alcohol. Lithium aluminum hydride can also reduce alkanoic acid, is what's used here to reduce this alkanoic acid to an alkanol. Okay, that's our reducing agent. The last reaction involving these alkanoic acids are the formation of alkanoates, or those are esters we talked about before. And so what happens is the acid has to react with an alkanol. Okay, so we have an alkanoic acid, so we have a C double bond O, OH group, and an alkanol, some other alkyl group with an OH on it. And what happens is we remove water. Okay, so we're going to remove this OH and this H to form water. And then this R prime group will bond here with this single bond O. So we have R group, our alkyl group, single bonded to carbon. This carbon is double bonded to an oxygen and also single bonded to another oxygen. And then that oxygen single bonds to this second alkyl group, which we call R prime. Here's an example of that with CH3, CH2, C, double bond O, single bond OH, reacting with methanol. So we remove this H and this OH, and the CH3 will bond to the O in the alkanoic acid. Okay, and this is methyl propanoate. Methyl propanoate. And I think I've talked before about the naming of these, but just as a reminder, the structure looks like this. Let me draw it for you. This is a single bond. So this is our parent, right? And what happens is whatever is bonded to the oxygen on the other side, we consider a substituent. So we name that first, methyl. And then we have a 1, 2, 3 carbon parent chain. So this is propan. And then because we have this double bond O, single bond O structure, this is an OATE because it's an alkanoate. So we formed methyl propanoate in this case. The fourth kind of reaction that acids can undergo are neutralization reactions. So when an alkanoic acid is reacted with alkali metal hydroxides, like you see in the reaction below of CH3 COOH with sodium hydroxide NaOH, the acid donates a proton. It donates this H plus proton. And the base, the hydroxide on the base, accepts it. So we end up with the sodium salt and water. Another type of reaction that acids can undergo is a reaction with carbonate or bicarbonate. So you can see here a reaction. Here's an acid, CH3COOH in both cases. Here reacting with sodium carbonate. In the second example, reacting with sodium bicarbonate. In both cases, the sodium binds with the deprotonated acid, and then the products additionally are carbon dioxide and water. All right, let's finally talk about reactions that happen involving those alkanoates. So we talked in the previous few slides about the formation of alkanoates. The reverse of that esterification process is hydrolysis or saponification. Alkanoates undergo hydrolysis in the presence of alkali metal hydroxides or strong bases. So group 1 alkali metals, sodium, potassium, hydroxides, to produce an alcohol and an alkoxide salt. This reaction is known as saponification and is an important process of soap making. So here is our alkanoate, and just for a visual, it's our alkyl group, our carbon, our carbonyl, so our double bond oxygen, single bond oxygen, and then whatever our second alkyl group is, R prime. Okay, so this R group can be a long chain carboxylic acids originated from animal fat or benzene derivatives and the resulting sodium or potassium salt in that soap. So look at what we end up with as our products. We have a cleavage that happens right here, okay? And so this stays the same, but it becomes an ion. It's a negative ion. And then the sodium or whatever the group 1 is, potassium, so the positive salt. And then we have this alcohol where it's the R prime, and then the OH group from the strong base. Let's talk a little more about this soap making process via the saponification that we just discussed. Soap making starts with fats and oils. Fats and oils are triesters of fatty acids and glycerol, a triol. Fats or oils are treated with strong bases like sodium hydroxide or potassium hydroxide that break down the linkages in the fats and oils. With a sodium salt, a hard soap is produced, and with a potassium salt, a soft soap is produced. So in the top image is a zoomed in image of a fat molecule from like an oil sample, okay? So we have these 3 long hydrocarbon chains of the fatty acids that have these alkanoate groups, right? So C double bond O with a single bond O to some R prime, right? And if we lyse this with the strong base NaOH, we break right here, right? That's where our hydrolysis occurs. And we end up with glycerol and the sodium salt of the fatty acid. So at every one of these places, we would have a negative ion, and the sodium positive ion forms the sodium salt. And then glycerol is our other product. Soap made with NaOH will have a higher melting point, which will result in a hard soap, than soap made with potassium hydroxide, KOH. That would be a soft soap. However, the solubility could be the reason sodium salt soaps are hard and potassium soaps are soft. Sodium salt soaps are less soluble in water than potassium salt soaps. It's because of the difference in charge density of the sodium ion and the potassium ion. The smaller size of the sodium ion makes the charge density greater. The greater charge density causes the sodium ion to be more strongly attracted to the fatty acid than the potassium ion. The enthalpy of hydration for sodium has a higher value than potassium. That means that sodium is less likely to hydrolyze because it requires more energy, more enthalpy. Another factor in the difference between a hard soap and a soft soap depends on if there are excess fats during the saponification process. The leftover fats will plasticize, making the soap hard. The source of fatty acid can also impact whether the soap is hard or soft. Animal fat will give a hard soap, while vegetable oil will form a soft soap. The polyunsaturated triglycerides have weaker intermolecular attractions, resulting in a lower melting point or a softer soap. Saponification is also used in fire extinguishers. Fire extinguishers used to put out grease fires are using this saponification process. Spraying the fire extinguisher turns the fats and oils in the grease to soap, making it no longer flammable. The reaction happens to be endothermic, further enhancing the effectiveness of the fire extinguisher. The reaction draws heat from the flames, lowering the temperature of the fire.